Welcome to the lecture series Damage in Metal Forming. Today we're going to speak about damage mechanisms. On this slide you see a description of how to use this material. I would like to ask you to carefully read these instructions and also to follow them accordingly. Thank you very much. You know that our lecture is divided into a total number of 5 topics. So today the topic will be damage mechanisms. And this chapter of damage mechanisms is subdivided into 5 tasks. The first 3 are related to the introduction to damage mechanisms, whereas the last 2 ones are related to the topic of fatigue. And I also would like to remind you of the color coding that applies. Content in green means we reach the advanced bachelor level. Content in yellow means we are reaching out even to the master's level, whereas finally red stands for reaching out to the PhD level. Now, the first thing to address is the simple fact that damage is not failure. Failure in general is a situation in which a component or a system stops to comply with its service requirement, and very often failure is reached because of fracture of the component. In contrast to that, damage is the evolution of the degradation of material properties related to microstructural changes that are very often referred to as the increase in porosity. So imagine you've got a part which is made of a ductile metallic material. Then you have to expect that this material contains inhomogeneities, like for example non-metallic inclusions. And these inhomogeneities very often play the role of nucleation sites for voids that evolve during plastic deformation. So the voids grow until finally we even run into a coalescence phase. These schematics can even be visualized based on real materials. So here you see the example of a dual phase steel of grade DP800, which is composed of a ferritic matrix and a hard martensitic second phase, which is found as islands in this ductile matrix. And if you deform this material, perhaps it was delivered as a sheet material and then it runs through a bending process, then you will see the nucleation of growth of voids, as it is indicated over here, until finally you even run into the coalescence phase, and that means that sooner or later fracture will be triggered. The learning outcomes for today are, on the one hand, to shed light on the evolution of ductile damage during forming operations, but then afterwards to discuss which failure mechanisms might interact with the forming induced damage when it comes to the service phase of the entire component. And that mechanisms that can be cleavage fracture, ductile fracture as well, or even fatigue. We are going to start with the evolution of damage, but I would still like to continue explaining what exactly that means that I've shown on the previous slide. So imagine you've got a situation in which you've got a material which first runs through a couple of forming processes. For example, processes that are established to have semi-finished products. These processes could, for example, be hot and cold flat rolling. And afterwards, you've got the service behavior of the component with individual conditions. And these conditions might be characterized by the fact that even ductile damage mechanisms might be triggered, but then usually under different boundary conditions compared to the initial situation in the forming processes. These boundary conditions could, for example, be strain rates or states of stress. Alternatively, a component could also experience fatigue loads. And then we have to speak about a mechanism interaction between ductile damage activated during the process of forming and cyclic material loads resulting in the activation of corresponding mechanisms during the service phase. And finally, a mechanism interaction between ductile damage during forming and cleavage fracture during the service behavior of the component, usually triggered because the temperatures that the component experiences are relatively cold. Now, having this in mind, we can also argue that the performance then is the load carrying capacity of a component in the critical load case related to the weight of the component. Having now this understood, we can ask key questions for which we have to find the answers. And these questions are: with what methods can we evaluate the performance of a component, which is produced by forming processes? And afterwards, how can it be shown that damage control during forming will really lead to a higher performance, especially when the underlying mechanisms change? So does it really make sense, in other words, to reduce ductile damage during forming by finding damage-controlled forming processes if later on fatigue loads become dominant for the service behavior of the component? So here we need to answer the question, do we have an interaction between those mechanisms? And what is the impact of this interaction? Anyway, we are going to start with those mechanisms that can be activated during the forming operations. We've already touched upon that point earlier, but I would still like to repeat what is going to happen. So here you see again the initial configuration of the matrix, including some inclusions, and then as a result of plastic deformation, voids are formed. They get enlarged until finally the material runs into the coalescence phase. But there's also experimental evidence. So here you see the nucleation of voids at this inclusion, and you even see the growth of these voids. What you do not see is the coalescence, but that is now something we found in literature over here. And you see how these cracks evolve between the initial voids over here. Previously, you have seen the mechanism of decohesion that results in void nucleation. So it will be shown again over here. And indeed, we see a decohesion between the inclusion and the matrix, and that results in nucleation of a void. Alternatively, in particular, we observe this in the dual phase steels. There could be cracking of the harder phase, in that case of the martensite phase. So you have to concentrate on this position over here. And you see indeed, due to the cracking of the martensite in this microstructure, in this dual phase microstructure, we observe the initiation of damage. So therefore, we could now draw the conclusion that we've got different mechanisms. One is the void nucleation by decohesion, for example, between matrix and particles, or at grain boundaries, or at phase boundaries, with the experimental evidence for that or these mechanisms on the bottom line over here, or void nucleation by cracking of the harder and stiffer constituents, like for example in non-metallic inclusions, in precipitates, or for second phases, And again, experimental evidence is given on the bottom line on this slide. Of course, the state of stress that is applied also plays a role. Very often, experiments are performed in uniaxial tensile loading conditions, which means that we have a very simple in situ loading condition for our samples. If you now change to biaxial testing as it is given over here, you could, for this dual phase steel, argue that now this splitting of the martensite island over here really classifies the corresponding nucleation mechanism as a martensite cracking event. But you also observe that now the nucleation let's say event is perpendicular to the resulting highest tensile loads that are applied, which are under 45 degrees as it is indicated here, compared to the axis of this diagram. And this means also that we understand that simply exceeding a critical fracture stress of the microstructural constituent martensite by the highest tensile stresses is the criterion to be used to predict this behavior. What are now the influencing parameters on void nucleation? Of course, extrinsic parameters need to be considered, in particular the state of stress. On top of that, we've also got some internal variables like individual morphological structures or properties that determine by which mechanism the nucleation happens. For example, if you increase the matrix yield strength, then the mismatch between the individual properties of matrix and particle is decreased, and that means you can reach higher stresses in the particle without running into the decohesion, so that it gets more likely that cracking of the hard second phase becomes the dominant mechanism. The same holds true for increasing the matrix hardening exponent. You have less decohesion and more second particle cracking. Likewise, you understand how to read this table. And here you see that we've got also a couple of intrinsic and some further extrinsic parameters for which we have found those relationships. Let's have a closer look at the modern DP steels. The main mechanisms in these dual phase steels are the martensite cracking, which is the number one, the ferrite martensite interface decohesion, which is obviously highlighted as a number 3 over here, so there's a mistake on this slide for which I have to apologize, or the ferrite grain boundary decohesion like given in this example. And now we figured out that there are a couple of factors that mainly control which of those mechanisms is dominant. One of them is the morphology of the martensite phase, which we address with size, shape, and distribution. The second one is the martensite volume fraction. And the third one and final one is the ratio of the yield stress of the ferrite compared to the yield stress of the martensite. So the mismatch or the contrast of the individual mechanical properties of the microstructure constituents. Number 1 is dominant for coarse-grained dual-phase steels, whereas number 2, the ferrite martensite interface decohesion, is dominant for the ultra-fine grain DP steels. Furthermore, it's also reported in literature that the number 2, the ferrite martensite interface decohesion, is dominant for low intermediate levels of martensite volume fraction, whereas the numbers 1 and also 3 are dominant for high levels of Martensite volume fraction. That was the nucleation phase. Now let's go to the growth phase. From the mechanical viewpoint, it is clear that we have to distinguish between loads, mechanical loads that lead to an increase in the volume of the pore, and mechanisms that lead to a change in the shape of the voids. So usually both happens at the same time. Therefore, you see the plus over here, and this would then be resulting evolution of the voids. It's also clear that the extrinsic stress state usually triggers whether or not growth takes place, and also determines by which mechanisms that happen. And experimental findings have shown that it's mainly the amount of hydrostatic stress that leads to the increase in volume, and the deviatoric stresses which lead to the shape distortion. Some in situ observations are shown here for the steel 16 manganese chrome sulfur 5, which is the case hardening steel, or a case hardening steel, that has been the second material under study in the first two phases of Transregio 188. And here you see in this movie the nucleation and growth of voids inside a manganese sulfide inclusion in this case hardening steel. And we can argue that, okay, obviously the damage itself looks different compared to what we have observed in the DP steel. On the other hand, we see similarities because, again, it's the harder phase, harder second phase, that causes the void to be formed, simply because the harder phase breaks. So here we observe that the uniaxial tensile deformation mode leads to the creation of a crack that is perpendicular to the loading direction. So again, this first principle stress criterion could be useful. And we also see that at high strains, the interface between the inclusion of manganese sulfide and the surrounding phase delaminates, leading to additional voids. Okay. Of course, we can also do corresponding experiments for the dual phase steel of grade DP800. Here's the video for this. And here you see a combination of tensile and compression tests. So we are investigating the role of different strain paths over here, where we started with uniaxial tension and then ran into a compression load. And we observe that the previously opened voids are then reduced in size during the compression phase. And of course, they also change their morphology during this compression. Some of the voids are even shrinking so much that we don't observe them anymore, at least with the applied resolution. But we also have to state that it remains unclear whether the voids will be closed even up to an atomic level, or if relatively small voids, too small to be seen with the resolution we have at hand, still remain. Now we run into the mechanisms of void coalescence. And usually it is reported that at least two mechanisms exist in the void coalescence phase, and that is on the one hand the necking of voids, and on the other hand the shearing, which could either be the interstitial ligament shearing or number B, the void sheet formation. Number 2A, the interstitial ligament shearing, is characterized by nucleation of a few voids and subsequent growth along this shear zone. Whereas the number 2B is characterized by the nucleation of many voids in such close proximity that they coalesce after relatively little growth. Okay, so it's all about the nucleation of secondary voids in this case. If we now look to another material, namely aluminum, we observe that the length over which the coalescence takes place is large if the matrix is hard and small for soft matrices. So here's the comparison and the experimental evidence for this statement. You see in the soft aluminum matrix, we've reached a deformation degree of 0.6 to observe the interstitial ligament shearing, whereas for the hard aluminum matrix, already at a phi of 0.15, we saw the void sheet formation and also the cracking-based nucleation. These were the mechanisms that are triggered during the forming processes. And now we come to the second point, and this is what happens during the service. Please remember that we said it can be a continuation of ductile damage, fatigue, or even cleavage mechanisms could be triggered, and the corresponding questions to be answered here. These green bars have been discussed previously, so I'm not going to continue over here anymore. Okay, now failure types obviously could be cleavage, ductile, or fatigue, but fatigue, that will be discussed afterwards by my colleague, so I will concentrate on these two mechanisms. A highly ductile material will show a very pronounced necking before failure, and finally this necking, which is a reduction in the cross section due to the extremely high ductility of the material, will continue until the remaining cross section is 0. So we do not even activate the mechanisms of void initiation, nucleation, growth, and coalescence. That happens in steel at very specific conditions. Most important is at extremely high temperatures. Most steels at moderate temperatures show a certain amount of necking, and then ductile damage mechanisms are triggered, which results in this fracture behavior that is displayed in a schematic overview over here. Whereas brittle fracture is triggered with nearly no necking in very many cases and with fracture surfaces perpendicular to the loading direction. What is now the underlying mechanism of the cleavage fracture, which results in relatively brittle material behavior? The underlying mechanism is twofold. At first, we are producing tiny micro defects as a result of the applied stress, like here in this ferritic pearlitic steel, where a crack has run through the pearlite. And this crack now has concentrated stresses at its tip, mainly over here, but of course also over here. And then finally, the local stress, the local tensile stress was sufficiently high to provoke unstable crack propagation. And then if you have a closer look at this, the fracture surfaces usually look as they are shown over here. So there is a significant microstructural influence present, and at a very high level of internal cleanness, we can argue that we need a strain-based criterion to predict the creation of those micro defects. Whereas in order to quantitatively assess the unstable crack propagation, we have to concentrate on the amount of tensile stress at the tip of those defects. And this means we need a stress-based fracture initiation criterion. And usually we observe a very high crack propagation speed and an abrupt failure. And that is due to the fact that, let's say, that the crack is fed by the energy that is released when the crack propagates. Here you see then the schematic overview of that mechanism. So you see the micro defect formation, very often triggered by fracture of a hard second phase, like a carbide precipitate. Outcome is micro defects. We also observe that the higher the local plastic strain, the higher the number of defects will be. But if then the applied tensile stress is sufficiently high, we run into phase 2, which is the unstable crack growth due to sufficiently high tensile stresses. If we have a closer look at the corresponding fracture surfaces, we see that the cracks either propagate along the grain boundaries, then we call them intergranular cleavage fractures, or across the grains, then we call this the transgranular fracture. The example you see over here of intergranular cleavage fracture was due to making use of phosphor as an alloying element in the corresponding steel. Phosphor tends to segregate at grain boundaries, which weakens the grain boundaries, and that has led to the observation that the crack propagated along the grain boundaries. It means that we need to characterize the tensile stress that a sample can withstand without triggering cleavage fracture. So what you can do to determine this very characteristic material property, you can perform tensile experiments at sufficiently cold temperatures so that it is very likely, at least for BCC steels, that you will trigger cleavage fracture. So you perform those experiments and you measure the applied forces or displacements, and then you simulate the experiments with the help of the finite element method. And for the critical applied loads, usually expressed in terms of applied force or applied displacement, and for the spot for which you have observed the initiation of the cleavage fracture, you evaluate the applied tensile stress. And if you do this accordingly, then very often you figure out that this so-called cleavage fracture stress shows a slight temperature dependence as it is indicated over here. Another problem with this is that there is a lot of scatter of the cleavage fracture stress. So if you perform multiple experiments, you will see that the critical stress that you applied on the sample differs a lot. In this example, from 1,462 megapascal to 2,205. So you also need statistical approaches, but they will not be discussed in detail in this lecture. Of course, also ductile fracture could simply be continued during the operation phase of the component. And now let's look what will be the decisive case that governs which of the two mechanisms will really come into play. So let us assume that on the one hand, we've got, as it was previously indicated, the cleavage fracture stress, which is slightly temperature dependent. But on the other hand, we've also got the yield stress of the component. which shows a more pronounced temperature sensitivity. In loading case number 1, at relatively cold temperature, we increase the stress by loading our sample. And before we even reach the yield strength of the material, we run against the cleavage fracture stress. So that is a situation in which cleavage fracture will be triggered after simple elastic loading. If we load our material at temperatures which are slightly above this intersection temperature over here, we will first run into the yield stress of the material, meaning we will have a small amount of plastic deformation, in which, however, not the entire processes of ductile damage can be activated. And that means after a certain amount of hardening, we reach the cleavage fracture stress of the component. If we now increase the temperature even further, then relatively early, we will reach the yield stress of the material. But then there is a relatively huge amount of hardening necessary to reach the level of the cleavage fracture stress. And this huge amount of hardening to be achieved also means we need high amounts of plastic strains. And that means there is enough driving force for ductile damage to evolve until even we run into the coalescence phase. And that's then a material behavior in which you observe the pure ductile behavior. And that means at such high levels of plastic strain, we see the initiation of ductile damage, which is to be characterized by the phases of void nucleation, growth, and coalescence. Of course, there are, again, different microstructural aspects to be considered, which is, as indicated before, the nucleation phase to be distinguished between decohesion at phase boundaries, or let's say in general at interfaces, or the nucleation due to breakage of the hard particles. In dual phase steels, many different mechanisms can be activated at different spots and at different loading conditions. But finally, I would like to mention that there's even a possibility for micromechanical characterization of the damage processes. Here you see the initial state, and then the damage accumulation in the second stage. And with XFEM modeling, we were able to describe the fracture of the martensite that then created a small void over here. But due to the fact that now martensite was broken, ductile damage was triggered in the surrounding soft ferrite. And with this, I would now like to come to the second part of the presentation, which will be introduced by my colleague Lars Lingner. Thank you very much.
Now we'll come to the subject of fatigue, where I briefly describe what is meant by fatigue in general, which parameters are relevant to it, and how the form-induced ductile damage in form of pores or voids affect the fatigue properties in general. On this slide, I will briefly introduce you to the characteristic parameters of fatigue loading and to show you why fatigue is a very critical topic regarding the failure of components. This is because damage or failure can occur at stress maxima below the yield stress or yield strength determined in tensile test. So it becomes very clear why this is so important and a dangerous topic regarding the failure of components. Various test approaches are used to study this fatigue behavior. Conventionally, or oftentimes constant amplitude tests with the type of stress can have different forms, like triangular or sinusoidal, which are fixed in advance of the test, are used. In this example, I will show you a sinusoidal load case that is stress controlled. The total stress is made up of the mean stress and the stress amplitude. This stress is applied repeatedly until it breaks or a specific termination criterion is reached. The stress amplitude, mean stress, and test frequency remain constant throughout the whole test. There are also different forms of like test parameters or test control parameters where, for example, the specimens are not stress controlled but strain controlled. But this I will discuss on the next slide. Then there's the so-called upper stress and lower stress, which are the highest or respectively lowest stresses in the whole fatigue test. Then there's the stress amplitude, which is the difference between the upper stress and the mean stress. The so-called working stroke is simply 2 times the stress amplitude. To go back to the type of test control that I already mentioned, I would like to describe the type of tests on the next slide. There we can see the different types of control variables like stress-controlled, total strain-controlled, or plastic strain-controlled tests. Then there's the so-called load condition, which is the ratio of the lower stress and the upper stress. If this is -1, it means there's no mean stress, and if it's not equal to -1, there will be a mean stress on the fatigue test. In addition to the before described constant amplitude tests, there are also multi-stage fatigue tests where the amplitudes and possibly the mean stresses are varied. Also, there are so-called service life time curves that resemble the real stress collectives of the components. The test frequency that are investigated depends on the load case of the real component. And for example, with servo hydraulic testing systems, we can achieve frequencies between 5 and up to 1 kilohertz in specific cases. For like very high frequencies, we can use ultrasonic testing systems, which have frequencies up to 20 kilohertz. Depending on the lattice structures of the material, typical ranges that are tested regarding the fatigue behavior are 2 times 10 to the power of 6 for cubic body-centered lattice structures, or 2 times the power of 10 to the power of 8 for cubic face-centered structures. In addition to that, relevant temperature ranges up to 1200 degrees Celsius are oftentimes included if this is a specific requirement for the use of the real component. An overview of the described control parameters and the influence regarding the material response and also the progression of the material responses over the lifetime of the component or the specimen can be seen here. Here are examples of stress-controlled, total strain-controlled, and also plastic strain-controlled tests, which I've described before. Now I'll show you some examples of influencing factors regarding the fatigue lifetime. For example, the material. Is the material like cubic body-centered? We get the graph number 1, and if it's cubic face-centered, we get the graph number 2. Then there's the type of loading. Is this torsional loading? Is it tension compression loading, or is it bending? Another influencing factor is like the surface. Is it a rough surface or a polished surface? A rough surface leads to, in this case, or in general, to a reduction of the lifetime. Then there's the geometry. Are the notches? Is this a solid rod? Is this a notched rod? Then the environment, for example, is there corrosion, no corrosion? Is it in vacuum or normal pressure? Like all these factors influence the fatigue properties in general. But oftentimes, like the microstructural damage, for example, in our case, the voids are not described. Another very important part is superimposed so-called static loading. So far, I've described sinusoidal loading without the mean stress. But in the practice or in the reality, oftentimes there's an additional superimposed static loading. This is in fatigue testing done by the implementation of the mean stress. Then we can get the stress amplitude, mean stress, and stress ratio, as you can see in these quotations. But in general, like the addition of the mean stress has no influence regarding the rest of the test parameters. For example, the constant frequency is comparable to the fatigue testing without a mean stress. Now I'll show you some of the typical Wöhler curves or SN curves, where we can see the different areas of the fatigue. For example, on the left, we can see SN curve from type 1 or type on the right side also, but on the left side, we can see the different areas like the LCF area, the low cycle fatigue area with the conventional fatigue lives, which are shown above, and the high cycle fatigue area, HCF, and very high cycle fatigue area regarding the different number of cycles to failure. We can also see that in the low cycle fatigue and high cycle fatigue area, the surface cracks are more important regarding the damage initiation. However, the influence is most important in the low cycle fatigue area. In the very high cycle fatigue area, there's more importance regarding damages inside the volume, like internal cracks. For our case of the TRR, where we have the voids inside the volume, this will also be a very important topic regarding the investigation of the very high cycle fatigue damage mechanisms and the interaction with the forming-induced damage. On the right side of the type 1 curve, we can see the influence of the mean stress. Is the mean stress very high, we will get a shorter lifetime. If the mean stress is very low, we are like in the compression area, then there will be a higher lifetime because the crack propagation will be hindered. Now we'll discuss some parameters that influence the fatigue property or the fatigue stress in general. The influencing values can be summarized to form Moynihan group. There's the material load, where parameters like stress condition, load time function, temperature, frequency, load sequence, etc. In this case, we will discuss it later on, where we look at the axial torsional load cases and the load path dependence. And then there's material conditions, like what is the yield stress, and what is the surface, heat treatment, material defects, etc. Then there's the material geometry, size, shape, other notches, which have a high influence regarding the crack initiation and therefore the crack propagation and the damage mechanisms in general. And the material environment. Is there corrosive media? What are the temperatures? For example, for cubic body-centered cell structures, there's a higher impact of the testing temperature in comparison to cubic face-centered lattice structures. In this case, I will show you some examples that I've already described to give you an overview of different influencing parameters that can be controlled throughout the test. For example, in our case, we will discuss later on the influence of the environment. In this case, very low temperatures regarding the influence on the fatigue behavior or fatigue properties. And in this case, we can see like visual representation of the described parameter influences, for example, temperatures, and also like the yield strength and the influences of the environment like corrosion, which leads to a significant worse fatigue property. Now we'll come to the parameters that influence the fatigue properties that are very important for our investigations within the TRR. We have the push-pull endurance limit or the tension compression, the torque endurance limit, which we test with torsion testing, and the bending endurance limit by, for example, rotating bending. Then there's also like the load collectives. This is triangular, sinusoidal, or a different form of stress. And we can see that, for example, the sinusoidal is like in the middle way of the damage, because with triangular stress collectives, we have very few peaks or like higher stresses regarding the influence on crack propagation in comparison to sinusoidal or different forms. And this is also described within that the load time functions vary in the load rates per cycle. And also we can see that square or sinusoidal load time functions show higher load rates per cycle than triangle load time functions. This leads to dislocation movements that depends on the load rates per cycle. A higher load rate in general results in an increasing movement of dislocation, and this is the cause of the increasing plastic deformation within each load case. Then we will come to the microstructural changes during cycle loading. The process of it is divided into 4 different stages. In stage 1, we have the so-called cyclic softening or cyclic hardening regarding the different materials and material states, in which the volume of the specimen, or like in the whole volume of the specimen, the dislocations movement starts. We have, for example, a formation of dislocation structures. Then we have the area 2. This is the microcrack area, where macrocrack is formed and slowly develops to a macrocrack on the specimen surface. In area 3, we have a continuous macrocrack propagation. Area 4 is like an instable area where we have the final fracture, where we exceed the tensile strength and residual cross section. Now we'll show you some examples of the microstructural changes during cycle loading. For example, the strengthening, which is the increasing resistance against dislocation sliding. We have different mechanisms that are relevant for the dislocation movement, like wave hardening, which is an increase in dislocation density. This is done through gold forming, for example. In our case, full forward work extrusion in the forming process leads to a dislocation density increase in the 60 manganese chrome S5. Other mechanisms such as grown boundary strengthening, mixed crystal hardening, and precipitation hardening are also relevant mechanisms, but not for the 60 manganese chrome S5. So I will come to the torsional fatigue tests with the 60 manganese chrome S5 that are done within the TRR 188, or the fatigue test in general. We test torsional and also bending and tension compression, cyclic loading or fatigue tests. At first, I will start with some extra fatigue tests with the 60 manganese chrome S5. In this case, the low cycle fatigue. In this example, we tested the specimen with a total strain control test with an amplitude of 1%, with 2 different damage states that depend on the shoulder opening angle. We tested the shoulder opening angle of 30 degrees and 90 degrees. The shoulder opening angle of 90 degrees has, in general, more forming-induced damage in comparison to the shoulder opening angle of 30 degrees. This is also be seen in the low cycle fatigue test, where we can see that the tests with a shoulder opening of 30 degrees have a better lifetime or higher lifetime or high number of cycles in comparison to the shoulder opening of 90 degrees. Also, this test data was used to calibrate a simulative model to predict the fatigue performance regarding the initial forming-induced ductile damage. And in this case, we tried to couple the experimental results with simulative models for the damage-dependent performance prediction. And regarding this, we saw that the influence of the forming induced damage on the fatigue properties is clearly given and significant. We also see that within the hysteresis that there's a cyclic softening. In this case, we can see for both shoulder opening angles on the left 30 degrees and on the right 90 degrees that for both initial damage states, we see that over the lifetime of the component, there's cyclic softening. This is a combination of the strain hardening or this, within the forming process of full forward ward extrusion, where we have like a formation of dislocations And within the cyclic loading or the fatigue loading, we have like a dislocation annihilation, which leads to a cyclic softening. Also, we use statistical methods for the assessments of the damage effect. After the testing, however, we look at the damage mechanisms and do factographic investigations to look at the influence of the forming-induced damage and how this leads to the crack initiation and propagation of the component. Typical for low cycle fatigue, like I've described before, we have many crack initiation sites because we're in the low cycle fatigue area. Also, we can see the ferritic and pearlitic microstructure of the 60-manganese chromos 5, as well as so-called manganese sulfides. Typical for like fatigue loading, we see different damage areas. We have typical ductile fracture morphologies as well as fatigue morphologies. Also, we can see the influence of the manganese sulfides and the formation of pores regarding the crack initiation and crack propagation, because nearly all crack initiation points were at pores or manganese sulfides at the surface area of the components or the specimens. So we try to evaluate the stress-dependent damage mechanisms. For this, another colleague did anaxial fatigue strength testing on other material, in this case the DP800 material. And these test data were compared to real LSN curves that are generated for different damage states and degrees of deformation. In this case, we compared to the damage states of shoulder opening of 90 degrees and a degree of deformation of 0.5. We can also see that different degrees of deformation leads to different fatigue properties. Like in this case, the red graph has a degree of deformation of 1.0 and has fewer voids within the volume, so the fatigue lifetime or the fatigue properties in general are better in comparison to the degree of deformation of 0.5. Some other measurement systems like micromagnetic sensors give a good correlation of the measurement data with the plastic strain amplitude of the extensometry. So these are like some examples of measurement systems or structure-sensitive measurement systems that are suitable of assessing the development of the damage within constant amplitude tests as well as stepwise load increase tests, like in this example. These can also be used, or like micromagnetic measurement systems can be used to detect the number of voids and compare the different damage states, like in this example. Also, another system that is currently used is resistometry based. This is a nano voltmeter measuring system in combination with the source measuring unit, which has a much higher reproducibility and accuracy in comparison to conventionally used direct potential drop current measurement systems. In this case, we can see that with the electrical resistance, we can differentiate between the different shoulder opening angles of 30 and 90 degrees, and therefore different damage initial damage states. This can also be used during the fatigue test, like in the example shown below, where intermittent fatigue tests were performed, where the tests were stopped and then measured with the nanovoltmeter system to assess damage development of the different shoulder opening angles and initial damage states. Now we'll come to the torque endurance limit, or the torsional fatigue test within the TRR 188. In this case, there's a comparison between different damage states. In this case, the shoulder opening angle of 30 degrees in the upper half and the shoulder opening angle of 90 degrees in the lower half of the page. There we can see that the different damage states lead to a different damage propagation within the fatigue test. We can see the number of torsional cycles to failure in this case is higher for shoulder opening of 90 degrees. This can also be seen within the axial deformation, rotation angle hysteresis that are shown on the right. So it was possible to analyze the damage evaluation as a result of the stress and damage states for uniaxial fatigue tests as well as torsional fatigue tests. And to understand which mechanisms are relevant regarding the crack initiation and crack propagation, we also did some fractographic investigations where you can see many longitudinal cracks on the surface of the specimen. Also, we have some radial ingrowing cracks regarding the fracture area of the specimen. So we can identify the failure relevant and dominant cracks regarding torsional fatigue testing, and also identify the different crack propagations. The last part that I will try to discuss is the axial torsional fatigue test within the TRR 188, where we have a superimposed torsion on top of the tension compression testing. There we see with like the change in resistance, which can describe the damage accumulation within the fatigue test, that an superimposed torsion in comparison to axial fatigue testing leads to a faster damage development. So we can evaluate that the superimposed stress on the material reactions leads to a faster damage accumulation and so to a faster crack propagation. So these structure sensitive measuring methods are suitable to describe and assess the damage development for different type of load cases and also different type of damage mechanisms. These investigations were evaluated by microstructural investigations. In this case, we used typical SEM methods as well as advanced SEM methods. For example, 3D image reconstruction using the focused ion beam secondary electron microscope, as well as SEM methods such as EBSD or electron contrast channeling imaging and scanning transmission electron microscopy. By looking at the fracture areas of the specimen, we saw that the fractographic investigation allows the differentiation of the stress-dependent failure mechanisms regarding the torsional failure mechanism and the tension compression failure mechanisms. As well as we can see that the manganese sulfides and the voids are of importance for each of the different stress types that are relevant that we investigated. Also, we evaluated the influence of the superimposed stresses on performance and microstructure. So after all, we can say that the superposition of stresses leads to a faster damage evaluation and to a very critical load collective regarding the crack initiation and crack propagation.